Today we're going to be doing section 6.1, inner product, length, and orthogonality. Not all linear systems have solutions. So let's look at example 1. Why is there no solution to this? Well, a of x is a point on the line spanned by 1, 2, and b is not on that line. So a of x does not equal vector b for all vectors x. Instead, find x hat so that a times x hat lies closest to vector b. Using the information we learn in this chapter, we will find that x hat is 1.40, so that a of x hat is 1.4 and 2.8. The segment joinin ax hat equals b is perpendicular or orthogonal to the set of all solutions ax equals b. We need to develop fundamental ideas of length, orthogonality, and orthogonal projections in this unit. The inner product or dot product of u and v. Here we have vector u and vector v. U dot b, the dot product, is equal to u transpose times v. Note that v dot u equals u dot v. Theorem 1. Let u, v, and w be vectors in Rn, and let c be any scalar. Then we have the following. U dot v equals v dot u. Vector u plus v dot w equals u dot w plus v dot w. C times vector u dot v equals c times u dot v, which equals u dot c times v. U dot u greater than or equal to 0, and u dot u equals 0 if and only if u is 0. Combining parts b and c, one can show the following. Length of a vector norm. For vector v, the length or norm of v is the non-negative scalar v, double absolute value of v defined by the following. So to find the norm of v is the square root of v dot v. And to find the norm of v squared, it would be v dot v. For example, if vector v was ab, then the norm of v would be the square root of a squared plus b squared, the distance between vector 0 and v. Distance in Rn. The distance between u and v in Rn is as follows. Distance uv is the norm of u minus v. This agrees with the usual formulas for R2 and R3. Let u be u1, u2, and v be v1, v2. Then u minus v equals u1 minus v1 and u2 minus v2. And the distance between u and v is the norm of u minus v, which is the norm of u1 minus v1, comma u2 minus v2, which is the square root of u1 minus v1 squared plus u2 minus v2 squared. And these should look familiar from previous math classes. Orthogonal vectors. So this is the proof of the law of cosine. So you should be seeing a lot of geometry here that you've used in the past in calculus, pre-calculus, algebra 2, and geometry. So the distance of uv squared is the norm of u minus v squared, which is the same as u minus v dot u minus v, which then would equal u dot u minus v plus negative v dot u minus v, which we would have u dot u minus u dot v plus negative v dot u plus v dot v, which would then equal the norm of u squared dot the norm of v squared minus 2u dot v. Similarly, we have this. Since the distance of u v squared equals the distance of u negative v squared, u dot v equals 0. Two vectors are orthogonal if and only if u dot v equals 0. Also note that u and v are orthogonal. If u and v are orthogonal, then the norm of u plus v squared equals the norm of u squared plus the norm of v squared. Theorem 2, the Pythagorean theorem. Two vectors u and v are orthogonal if and only if the norm of u plus v squared equals the norm of u squared plus the norm of v squared. Orthogonal complements. If a vector z is orthogonal to every vector in a subspace W of Rn, then vector z is said to be orthogonal to W. The set of vectors z such that there are orthogonal to W is called the orthogonal complement of W and is denoted with W to the perpendicular, read as W perp. Theorem 3. Let A be an m by n matrix, then the orthogonal complement of the row space of A is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. So row A perp equals null A, and column A perp equals null A transpose. To see the complete proof of this and why it is this way, you can go to your textbook. And it's on, if you have the hard copy, it's on page 381. Let's look at example 2. So we're going to let A be 1, 2, 0, 0, negative 1, negative 2. Find the following. So the basis for null A. When we row reduce and echelon form this, you would get x1 to equal x3, x2 would be free, and x3 would also be 3. Okay, so the basis for null A would end up being 0, 1, 0, and 1, 0, 1. And therefore, null A is a plane in R3. So the basis for row A. Again, when we get this in row reduced echelon form, we choose the non-zero row, and the basis for row A would end up being 1, 0, negative 1. And therefore, row A is a line in R3. Basis for column A. Column A would be the basis for column A would be your pivot column, and that would be your first column. So that would be 1, 2. And therefore, column A is a line in R2. Basis for null A transpose. So we need to go ahead and get A transpose. And A A transpose would be 1, 0, negative 1, 2, 0, negative 2. So we would need to use that for this. And when you get this into reduced row echelon form, you end up getting x1 equals negative 2x and x2 being free. So the basis for null A transpose would be negative 2, 1. And therefore, null A transpose is a line in R2. So showing this, subspaces of null A and row A are perps of subspaces of null A transpose in column A. So they're perps of each other. And this would be your row A and null A. Here you would have column A and A transpose.